guys, and welcome to another calculus video. In this video, we are going to be taking on this awesome generalized integral that you can see right here. It's the integral from 0 to infinity of x to the alpha minus x to the beta over ln x. And on the bottom, we also have the sum from k equals 0 to n of x to the k. So that would be 1 plus x squared plus x cubed, and so on and so forth. One thing that I want to note here is that we need negative 1 to be less than beta, which is less than alpha, which is less than n minus 1. And n should be greater than or equal to 1 and an element of the natural numbers. So that is our integral right here. It's a pretty interesting problem, I think, and I would definitely suggest you should stick around to the end because some of the special cases of this integral are absolutely magnificent. So let's go ahead and jump right into it. So this was inspired by Maths 505 because he recently evaluated one case of this integral, and it made me think that I should probably do the generalized case here because it's quite an interesting result. So first, we're going to use the fact that the integral from alpha to beta of x to the v dv gives us x to the alpha minus x to the beta over ln x, which is just this expression right here. So we sub that in, and we get the integral from 0 to infinity of the integral from alpha to beta of x to the v over the sum from k equals 0 to n of x to the k dv dx. Now, since the absolute value of this expression is the same as the expression, we can go ahead and apply Fubini's theorem because we know the original integral converges, so we can interchange the order of integration here. But the thing is, here on the bottom, this summation is a little bit nasty to deal with. So what we're actually going to do is we're going to take the sum from k equals 0 to n of x to the k. We're going to write it out, all these terms, and we multiply both sides by x minus 1. And then we multiply this by each term. So we're going to get x to the n plus 1 minus x to the n plus x to the n minus x to the n minus 1, so on and so forth for every term until we get to x minus 1. And every single one of these intermediate terms is going to cancel because of the next term in the series. So overall, we just get x to the n plus 1 minus 1. So we can go ahead and sub that into our integral. And now we're going to start to do a little bit of some interesting tricks here that you might not be familiar with, because this is actually a method that I haven't seen used too often, but it is something that I notice pretty easily because there is a very cool integral formula that we will be deriving in this video, and it's very useful across a lot of different types of integrals. So we're going to go ahead and jump right into it. So this is really the weirdest part of this integration. What we're going to do is we're going to split up we want to split the numerator to create two separate integrals, so split this x and 1, but we can't do that because each of those individual integrals would diverge because of the singularity at x equals 1. So what we're going to do is we're going to take the limit as epsilon goes to 0 plus, then we're going to split this up into two separate integrals, one from 0 to 1 minus epsilon, and one from 1 plus epsilon to infinity. And then we're going to go ahead and actually split these apart, and then we're going to get two separate integrals for each of these integrands. So the integral from 0 to 1 minus epsilon, and the integral from 1 plus epsilon to infinity for x to the v plus 1 and for x to the v. And essentially we're approaching the singularity at the same rate from the right and from the left. And essentially what this means is, if you know what the Cauchy principal value is, that's what we're actually doing. We're taking the Cauchy principal value of both of these integrals because we know that converges. If we just approach the singularity from the same rate at the left and right, then the infinite contributions will cancel with each other. So we can go ahead and calculate the Cauchy principal value and then subtract those Cauchy principal values, and it gives us back our original integral value. So usually we don't see much use of Cauchy principal values, again, because it's telling us what the value of the integral would be if it converged. But in this case, it actually tells us the exact value of our original integral, which is not exactly these integrals. So, pretty interesting. However, now we are left with the task of now we have to evaluate this Cauchy principal value integral, which, again, we don't really know many tools for evaluating Cauchy principal values because it's not something that we usually end up doing. So we need to calculate the principal value of the integral from 0 to infinity of x to the a over x to the b minus 1 dx, where negative 1 is less than a is less than b minus 1, and b is a natural number. So in this case, contour integration is going to be our method. Now, one thing I want to note is that there's a lot of methods to do this integral. Ramanujan's master theorem is definitely the quickest. It gets it done in, I don't know, 20 seconds, honestly. Complex partial fractions is also pretty nice, and there's other methods as well, but contour integration is more fun. So if you don't want to stick around for the contour integration, just go ahead and skip down until we finish that, and you can see the rest of the integral and all the cool results. So we're going to define our function f of z to be z to the a over z to the b minus 1, and we're defining the argument of z to be between 0 and 2 pi. So that means our branch cut is going to be right here on the positive real axis, but technically it's just below the positive real axis, so we can integrate on the positive real axis. And we're going to integrate over this contour here, which looks really nasty, but it's not actually that bad. So notice we're trying to calculate the Cauchy principal value, so that's why as we're going on the real axis here, notice that we approach z equals 1, and then we go on a small circle around it, and then we go up to infinity again. And we choose this tiny little circle, which we're calling gamma 1, such that it has equal distance epsilon on both sides, which means that if we add I11, which is this curve right here, and I12, those two are going to approach the singularity again at equal rates from both sides, and so we'll be able to get the Cauchy principal value from that. Then, of course, we have to avoid this singularity, of course, and then we go up around in this circular arc. Then we come back down, and this ray right here coming out from the origin is at an angle 2 pi over b from the real axis. And so we come back on this ray right here, and then we end up doing the same thing with the Cauchy principal value in the small circle. Over here, we sort of go around, and then we drop back down to the origin. So we have a lot of different segments of our contour here. I11, I12, I wrote I12 twice. This should be I21, and this should be I21 as well. But you guys get the idea, and then I22, as well as gamma 1, gamma 2, and capital gamma. So first, notice that I11 plus I12, we're approaching the singularity from equal rates, so this is just going to be equal the principal value of x to the a over x to the b minus 1 dx, which is just I. For the gamma integral, we're going to go ahead and bound it real quick, so the absolute value of the integral is less than the integral of the absolute value, is less than or equal to r to the a over r to the b minus 1. That's pretty simple to do using the triangle inequality. And so this is less than or equal to r to the a plus 1 over r to the b minus 1. And actually I should have included also 2 pi over b right here because we're talking about the length of this gamma curve, which is 2 pi over b. But we're not worried because this goes to 0 one way or another. So this just goes to 0. Then for these small circle integrals, we're going to use the, I call it the circular arc theorem. Basically the integral over an infinitesimally small circular arc of angle theta around a simple pole of order 1 is going to be I times theta times the residue of f of z at z0. And one important thing to note here is that when we're talking about the angle here, the angle is positive if we're traversing in the counterclockwise direction and negative if we're traversing in the clockwise direction, which is the case for this integral. So gamma 1 is negative I pi times the residue of f of z at 1. We do some quick limit things, some L'Hospital's rule, and we get negative I pi over b. Same story with gamma 2. Again, we just use L'Hospital's rule and evaluate this limit. And we end up getting negative I pi times e to the 2 pi I times a plus 1 over b all over b. And then we're going to evaluate I21 and I22, which again were these two integrals over the upper circular arc here, which give us another Cauchy principal value. So we let z equal e to the 2 pi I over b times x, and this is going to give us negative because we were coming out from the outer arc into the origin, so that's why there's this negative sign here. Negative the principal value of the integral from 0 to infinity of e to the 2 pi I over b times x to the a power times e to the 2 pi I over b from our differential times, and then all this on the bottom, and then this is just going to end up becoming x to the b because e to the 2 pi I over b to the b power is e to the 2 pi I, which is 1. And so overall, we just end up multiplying by constant here, and that constant is negative 2 pi I times a plus 1 over b times I. So if we add everything together, we get that I times 1 minus 2 pi I times a plus 1 over b. Now this just comes from I11, I22, I12, and I21. And then we subtract I pi over b times 1 plus e to the 2 pi I times a plus 1 over b. This comes from gamma 1 and gamma 2. This is going to be equal to 0 because actually our function was analytic everywhere inside of the contour. That's why we made those little circles around the residues sort of bent in towards the contour because then we wouldn't have to evaluate any residues inside the contour. So once we simplify this, we have I pi over b times 1 plus e to the 2 pi I a plus 1 minus that. Then we multiply by e to the negative pi I times a plus 1 over b on the top and bottom. And this ends up actually becoming cosine and sine, and we end up getting that the principal value of the integral from 0 to infinity of x to the a over x to the b minus 1 dx equals negative pi over b times cotangent of pi times a plus 1 over b. Now notice if we actually replace this minus 1 with a plus 1, we would get almost the exact same formula, and this cotangent would just be a cosecant, and we would drop this negative sign. So that's a pretty good sign that we did something correctly. So overall, what we're finally going to get is the integral from beta to alpha of negative pi over n plus 1 cotangent of pi times v plus 2 over n plus 1 plus pi over n plus 1 cotangent of pi v plus 1 over n plus 1 dv. And we just got this from our standard from our integral from earlier. We just plugged in this principal value formula right here. And integrating this is super easy because notice that pi and n plus 1 are also right here, so we just divide those right out. And the integral of cotangent is just natural log of sine. So we end up with this nice natural log expression for I of alpha, beta, and n. But we are not done because there are a lot of really, really cool special cases of this integral. So let me show you those. So we have natural log of all these sines of alpha plus 1, beta plus 1, beta plus 2, and all that stuff. So if we actually go ahead and plug in 2, 1, and 5, which is, I think, I don't know, it's pretty nice just seeing all the numbers up to 5 right here. We get x squared minus x over ln x times 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th. And we get a nice little rational argument here, natural log of 2/3. However, if we take it a little bit further, we get I of 7, 0, and 9. We get the integral from 0 to infinity of x to the 7 minus 1 over natural log of x times 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th all the way up to x to the 9th. We get natural log of root 5 times phi, the golden ratio, which I just think is absolutely cool. And this is absolutely the coolest identity with this function right here. If we take I of 13, 0, and 15, which as you can see, I haven't even written out the whole thing because there's so many terms on the bottom, we get natural log of 2 plus square root 2 plus square root 2. That's crazy. And in fact, we can actually extend this because of the weird properties of cosine theta over 2. If we let m be any positive integer greater than 1, or greater than 1, we get I is of 2 to the m minus 3, 0, 2 to the m minus 1, is natural log of 2 plus square root 2 plus square root 2 plus square root 2 plus square root 2, such that we have m minus 2 square roots, which I just think is absolutely crazy. I mean, if someone showed you one of these integrals, would you guess that this was going to be the result? No, of course not. So anyway, I hope you guys enjoyed this video. Honestly, I was surprised by the answers to these integrals as well. I mean, I figured I'd just come up with a generalized result. I didn't think I would have such nice answers at the end. But anyway, I hope you guys enjoyed the video. I hope to see you in my Discord or my YouTube comments. Yeah, I'll see you in the next video. Hope you enjoyed, and I'll see you next time.